This is Chapter 11, Section 4, the dissociation of weak acids and bases. In this section, we're going to talk more specifically about the dissociations of weak acids and bases. We're going to learn how to write the expressions for these dissociations in terms of the chemical equation, as well as the equilibrium constant. Remember that every acid-base reaction is really a transfer of a proton from one substance to another. This transfer of a proton is often reversible, especially in the case of weak acids and bases, and so really there's an equilibrium between these species. Remember that strong acids fully dissociate in water, and so there's no equilibrium to talk about in those cases. Weak acids, however, only partially dissociate, and so there is an equilibrium between the neutral, undissociated acid molecule and the ionized products that it forms. Since this is an equilibrium, you can write an equilibrium expression and an equilibrium constant just like you can for any other reversible reaction. Now, strictly speaking, some of the sections in the previous chapter are not really required according to the syllabus, but I included the sections about equilibrium constants because understanding them can help you to understand how weak acids work. Let's take a look at an example to see how this works. Here we have formic acid, which is HCHO2. This interacts with water to donate a proton and leave behind CHO2-. The water takes a proton and becomes H3O+. Obviously, this is a reversible equilibrium reaction because this is a weak acid. Just like for any equilibrium reaction, we can write an equilibrium constant. In the previous chapter, we called these constants Kc. Now, since we're dealing specifically with acid equilibrium, we call them Ka. Other than that, there's no real difference between the K value here and the equilibrium K in the previous chapter. If you remember from the previous chapter, the way that you construct this expression is to take the concentrations of the products, multiply them together, and put them over the concentrations of the reactants. In this case, we have the formate ion, CHO2-, that's the first product. The concentration of that multiplied by the concentration of hydronium, which is the second product, is divided by the concentration of HCHO2. That's the undissociated formic acid molecule. You'll notice that we left water out of this equation, and that's because water is a liquid. From the previous chapter, hopefully you remember that liquids and solids can both be left out of equilibrium expressions. The only things you need to include are aqueous solutions, which we have here, and gases, which are not really relevant to this chapter. So this expression here is the form of the acid dissociation constant for formic acid. This is an experimental value that we can measure, and when we do this, we find that formic acid has a dissociation constant of 1.8 times 10 to the minus 4. Obviously, this is a very small number. In fact, it's 0.00018, which is much, much less than 1, which is another indication that this is a weak acid. Remember that the equilibrium constant for a reaction tells us something about how far the reaction proceeds. In this case, we're dealing with a specific type of equilibrium constant called an acid dissociation constant, but it still tells us the same information. When the value of Ka is small, it means that the acid doesn't dissociate much at all. It leaves mostly neutral reactant acid molecules with very little ion being formed. When the value of Ka is large, it means that the acid dissociates a great deal and leaves mostly ions. Weak acids, therefore, have small Ka values, typically much, much less than 1, as we saw for formic acid on the previous slide. Strong acids have large values, and in fact, if you look up Ka values for acids, most tables that include strong acids will just say something like large or infinity next to the strong acids. This table lists some of the Ka values, the acid dissociation constants, for a variety of weak acids. We can see that the smallest values are down here at the bottom, where you have 10 to the minus 13. The largest values are up here, where you have 10 to the minus 3rd. It's still a pretty small number relative to 1, and so phosphoric acid, H3PO4, is still a weak acid, but of the acids in this list, phosphoric acid is the strongest. That's because it has the largest Ka value. This table just summarizes some of what we've just been talking about. So for example, strong acids fully dissociate, 100% of the acid dissociates in solution, which means their equilibrium lies totally towards the product side because they have a large Ka value. The conjugate base of a strong acid is going to be weak. The weak acid has an equilibrium that lies mostly towards the reactant side, towards the undissociated molecules. This is because Ka is small, indicating that only a small percentage of the acid dissociates. The conjugate base to a weak acid is going to be relatively strong. At the bottom of the chart, we can also see similar properties for strong bases and weak bases, but here they're characterized by a Kb value rather than a Ka value. This acts mostly the same as Ka, but we're not going to get into the details of how Kb works in this course. So if we're given any arbitrary acid, either by name or by formula, we should be able to write the acid dissociation expression for it. In other words, the form of the Ka equation. In order to do this, of course, we have to first write the chemical equation. To do that, we always assume that the acid reacts with water. In this case, you have HNO2, nitrous acid, and this would be dissolved in water, so we would give it an aqueous designation, and it's going to interact with the water molecule, which is typically in the liquid phase. This is going to cause a reaction where the HNO2 donates a proton to water, leaving behind an NO2- ion. This is the nitrite ion. H2O, having accepted a proton, becomes H3O+, and this is an ion, and so it is also aqueous. This is how we write the chemical equation for the dissociation of an acid. We always assume the acid to be donating a proton to a water molecule. Now, to write the equilibrium expression for this, the Ka value, we just have to look at the products and the reactants, getting rid of water, and put them into the expression that we learned in the last chapter. So the products go on top. We have the concentration of the first product, which is the nitrite ion, NO2-. This is going to be multiplied by the concentration of the other product, which is the hydronium ion, H3O+. These are divided by the concentration of HNO2, the nitrous acid. Remember, this is the undissociated form of nitrous acid. Notice that there are no exponents in any of this because the coefficients for all of these species in the equation are 1, and it balances out that way. Also, remember that we left out the H2O because H2O is in the liquid phase, and you can leave solids and liquids out of an acid dissociation expression.